Okay, let's go ahead and get started. Good stuff on the books today. Remember to pick up problem set 3, which will be due next week. Same time, same place. So let me just spend 1 minute discussing a little bit where we've been and where we're going in this class. So we spent about 2 weeks studying the kinematics of quantum mechanics. Before moving on to a discussion of time dependence in quantum mechanics, we discussed both the Schrödinger and Heisenberg formulation of quantum time evolution, and this led us to a consideration of the path integral. So what I would like to spend this next week doing is spending a bit of our time devoted to some simple quantum mechanical systems that you have probably seen before, but we will cover in a bit more detail and from a slightly different point of view. Before moving on next week to more advanced subjects, so this week will be the last week of the course where we do sort of a bit of a review of things that you've already seen before, and after this week it'll probably be largely new material. Next week, for example, we'll start our discussion of quantum statistical mechanics, entanglement and measurement theory, before moving on to the subject of symmetries in quantum mechanics, time-dependent perturbation theory, and relativistic quantum mechanics. But today, what I would like to do is spend a little time with our old friend, the simple harmonic oscillator. At this point in your physics careers, you've probably beaten the simple harmonic oscillator to death many, many times, beginning from your original physics courses to now your most advanced quantum classes. And there's a reason, which is that the simple harmonic oscillator is simply the most important system in physics. And indeed, Michael Peskin, a well-known particle physicist, has said once that physics is that subset of human experience which can be reduced to simple harmonic oscillators. And I really think there is a real core of truth in this way of, this is a slight exaggeration, but it's only a slight exaggeration. For example, all of particle physics, all of condensed matter physics, is essentially the study of simple harmonic oscillators and the perturbations thereof. They're very complicated harmonic oscillators. There are, in some cases, an infinite number of them, but they're harmonic oscillators nonetheless. Okay. So, by the way, let me just check. How many of you have seen the algebraic derivation of the spectrum of the harmonic oscillator in terms of raising and lowering operators? Okay. I assume that most of you have seen it before. We'll review it now very briefly because it's something that you should be able to do in your sleep. But I'm only going to spend a few brief moments on it. Okay. So let me just remind you that the harmonic oscillator is the system describing a particle in one dimension whose Hamiltonian is the sum of p squared and x squared. P squared being the usual kinetic term, x squared being the potential of a simple harmonic oscillator. And the way that we typically solve this system in quantum mechanics, well, there are a variety of ways. For example, one could just write down Schrödinger's equation and solve it. It's actually not too hard in this case. Or, as we saw last class, we could perform a path integral to compute the time evolution operator. But, as is often the case in physics, if there is an algebraic method that allows one to solve the system completely without ever using a differential equation or an integral or something like that, then that is often an extremely illuminating and extremely useful way of approaching the problem. The way that one does this is one defines a new operator A, which is referred to as the lowering or annihilation operator. This operator is a linear combination of x and p with a relative coefficient I, meaning that A is no longer Hermitian, so A dagger does not equal A and is usually referred to as the raising or creation operator. And together, A and A dagger are typically denoted or typically referred to as Fock space operators. And it's easy enough to check that our familiar fundamental commutation relation between x and p implies that A and A dagger also obey a commutation relation, namely that their commutator is equal to 1. That's easy enough to check simply by plugging the fundamental commutation relation, plugging in our definition of A and A dagger into the commutator of A and A dagger, and using the fundamental commutation relation. In terms of these operators A and A dagger, the Hamiltonian is A dagger A plus a constant times the frequency h bar omega. And this operator A dagger A is important enough that we typically give it a name. We call it the number operator. And that 1/2 comes from the reordering of A and A dagger. So one could also write the Hamiltonian as A dagger A, 1/2 A dagger A plus A dagger in a completely symmetric way. And given this fact, it's easy enough to see that an energy eigenstate is an eigenstate of the number operator n. And in order to understand the spectrum of the system, let's denote such an eigenstate by little n. And I will define these eigenstates to be unit normalized. Then, using the fundamental commutation relation, written in terms of the A's and A daggers, one can go ahead and ask, given an eigenstate of the number operator, what happens if you act on it with the raising or lowering operators A and A dagger? So what is n times A acting on an eigenstate? Well, that's A dagger A squared acting on the eigenstate. And one can then go ahead and commute the A dagger through in order to see that this is n minus 1 times A acting on it. So the lowering operator A, as advertised, reduces the eigenvalue of the number operator by 1. That's just a consequence of the algebra. Likewise, the raising operator does exactly what you would expect based on its name. This will give you an eigenstate of the number operator with one higher value of the eigenvalue. So we see that if you start with an eigenstate of the number operator, you can act with the A's and A daggers to change the eigenvalue of the number operator, i.e. the eigenvalue of the Hamiltonian. Now, one can use this observation to understand exactly what the spectrum of the Hamiltonian is, without ever solving any differential equation. How do you do that? Well, let's note that the number n, which is the eigenvalue of one of these states, is by definition the expectation value of the number operator in one of its eigenstates, which, by definition, just writing out the definition of the number operator, is the expectation value of A dagger A. And I can make this a little more suggestive by putting some parentheses here. So we see that this is in fact the norm of the state A acting on N, and hence it must be greater than or equal to 0. So we know that the expectation that the eigenvalue of the number operator must be positive or equal to 0. And we also know that acting with a lowering operator can lower the eigenvalue of the number operator. That means that if you have a state whose eigenvalue of the number operator is not an integer, you could keep lowering it until you got a negative number, which would violate this equation that I've written here. So what that means is that the allowed states are precisely given by non-negative integers. And the state with little n equals to 0 is going to be defined by the condition that it is annihilated by the lowering operator. Here I should make a little bit of a comment. The state here where I have the 0 inside the ket is not the null vector. It's not the null state in the Hilbert space. It is a physical state. It is the ground state of the harmonic oscillator, namely the state with the lowest eigenvalue of the Hamiltonian. This 0 here on the other side, however, is the null state in the Hilbert space, i.e. it is the state with 0 norm in the Hilbert space, as you would expect based on this equation here. So 0 is the ground state. Is this familiar so far? You guys have all seen this before. Given the ground state, the other operators are obtained by acting on the ground state with the raising operator. If you act n times on the ground state, you obtain a state with energy with eigenvalue n. And one just has to normalize this state appropriately. And it's a straightforward exercise in commutation relations to check that the way that you would normalize it appropriately is to include a factor of the square root of n factorial. That's an easy computation that I'll let you do yourselves if you haven't seen it before. Just as a bit of an aside to touch base with other descriptions of the harmonic oscillator which you have seen, is that it is easy in this basis, given this algebraic derivation, to write these states in the x representation, in the x basis. How would we go ahead and do so? Well, let's say that we wanted to write down the wave function of the ground state. Well, in order to do so, you just use the defining equation for the ground state, namely that it is annihilated by the lowering operator, and then you use the definition of the lowering operator. So this was x plus I p over, I think it was m omega. Unfortunately, I decided when I wrote my notes to use units where m is equal to 1, which means that every time I write a formula, I need to restore the factors of m using dimensional analysis. That's okay. It's what keeps me awake when I give lectures. And then we use the representation of the momentum operator in terms of the derivative. So this is in terms of the wave function of the ground state, x plus h bar over m omega times d by dx, acting on the ground state, is equal to 0. And this gives you a differential equation that is obeyed by the ground state wave function. In particular, the ground state wave function is a function such that when you take the derivative of that function with respect to x, you get m omega divided by h bar times x. And it's easy to solve that differential equation. It's just a Gaussian. In particular, let's just convince ourselves of that. if you took the derivative of that guy with respect to x, you would pull down a factor of minus x times m omega over 2 h bar times 2 because of the derivative of the x squared times x, which you can see would indeed be a solution of this differential equation. Okay. How do we then write down the, so this, of course, is the usual Gaussian solution of the time-independent Schrödinger equation for the simple harmonic oscillator. And one comment I will make in order to touch base with something that I'll be discussing later on in this lecture is that this is a minimum uncertainty state. Okay? The expectation value of delta x times the variance of delta x times delta p saturates the Heisenberg uncertainty relation in this state. In fact, and that is true for any value of the frequency omega. How then would one write down the wave function of a higher order state where the number operator is non-zero? Well, that is just found by acting with the raising operator. In particular, the raising operator to the nth power is just x minus h bar m omega times d by dx, viewed as a differential operator to the nth power. And if you take the Gaussian and you act with this differential operator on it n times, you will obtain the wave function for the harmonic oscillator in its nth state. And this gives you an exponential times some polynomial in x, which is known as a Hermite polynomial. In most traditional approaches to the simple harmonic oscillator, you start by solving the oscillator in position space and deriving the Hermite polynomials and having no understanding of what they are and what the heck they're doing there in the harmonic oscillator. That's why I think it's much clearer to think about it in algebraic terms, where the defining equation of the Hermite polynomial is simply the statement that it's the Gaussian acted on by the differential operator, which is the raising operator, n times. Questions so far? I would now like to tell you things that you don't know. Okay, well, I'll start by telling you one thing you do know before telling you why I should tell you things you don't know. Okay. The thing that you do know is that in one of these energy eigenstates, the expectation value of x and p is time independent. By definition, these n's are energy eigenstates. In the Schrödinger representation, x and p are operators that do not depend on time. Hence, their expectation values in these states do not depend on time. This is very unlike the classical solution of the harmonic oscillator. The classical solutions of the harmonic oscillator oscillate. It's right there in the name. So let us then ask, is there a state of the simple harmonic oscillator which more closely resembles our classical intuition? This is important because the states, the energy eigenstates n that I've described above, clearly are not going to go over in the limit where h bar goes to 0 to our semi-classical understanding of the harmonic oscillator as a system whose states oscillate in time. So if you ever want to make contact with classical physics, and we live in a classical world, essentially, so it's often important to understand the implications of quantum mechanics for classical physics, then we need to understand whether it's possible to study the states of the simple harmonic oscillator in a manner which makes clear that they oscillate in time. And indeed, there is a special family of states which have precisely this property. And they are known as the coherent states. And the defining property of a coherent state is not that it is annihilated by the lowering operator, which is the definition of the ground state, but rather that it is an eigenvalue of the lowering operator. And one thing, that's a lambda there, of course. One of the things that one should note about this definition is that according to this definition, lambda is not necessarily real. The eigenvalues of a Hermitian operator are real, but A is not Hermitian. So let's understand why it is that this new basis of states is the correct one to use if we wish to make contact with our classical intuitions. So let's write down the wave function for this state. So again, this is determined by just taking the inner product of the defining equation for the coherent state with x, and then the left-hand side of this equation can be written in a position space basis using the representation of A as a differential operator. And so you see that this turns into a differential equation that is obeyed by the wave function of the coherent state. Or, if I shuffle this around a little bit, it means that the wave function of the coherent state obeys a first-order differential equation saying that it is annihilated by not the operator d by dx plus x, as was the case for the ground state, but the operator d by dx plus x minus x naught, where x naught is equal to lambda times the square root of 2h bar over m omega, just from this earlier equation. So let's see how awake you guys are. Who can tell me what the solution of this is in 10 seconds or less? Oh, come on. Yes?
A Gaussian go with x replaced by x minus x.
Exactly. Okay. If you shift x by x naught, then this becomes precisely the wave equation for the ground state that I just solved for you 5 minutes ago. Good. So the wave function is some normalization factor times the exponential of minus m omega over 2h bar, just as for the ground state, times x minus x naught squared. There's an important subtlety here in thinking about this solution, which is that x naught here is complex. And so, if x naught were real, then this would just be a Gaussian that is displaced by some amount relative to the origin. But because lambda is complex, this state has a phase which varies as a function of x, and in particular, it goes like e to the I kx, where k is just the imaginary part of the quantity in the exponential, so it's m omega over h bar times the imaginary part of lambda. Just plugging in all of those definitions here. So you can see that there is a sense in which this wave function should describe a particle that is moving. I remind you that e to the ikx is the wave function of a particle that's moving with momentum k in the x direction. And I also remind you that because this is a Gaussian, this is a minimum uncertainty state. In that the product of the variance of the position and momentum operators in this state will saturate the Heisenberg inequality. And let me tell you another fact. This is a very easy fact to show. In fact, I don't remember if I asked you to show it on the next problem set. If I don't, I really should have. It was an oversight on my part. And you should all correct that oversight by proving it to yourselves. But it is a fact that's very easy to show that x of t in the coherent state is proportional to sine omega t. Okay, that's a good sign. That just comes, so there are a lot of different ways of deriving this. One way is to just use the commutation. Well, there are a lot of different ways of deriving this. I'll let you figure it out yourself. It's easy enough to show. And so what that means is that this state oscillates like a normal harmonic oscillator. I heard some muttering, maybe in confusion, based on the statement, so let me just make one more comment, of course, which is that a coherent state is an eigenvalue of A, but it is not a time-independent state. It's not an eigenvalue of the Hamiltonian. Okay. So for that reason, the coherent state will evolve in time, and its time evolution is just studied by, well, among other things, one could, for example, compute the time derivative of the expectation value of x dot using the Heisenberg equation of motion. In fact, I think you probably did that on one of your earlier problem sets. It's essentially the same equation here, and you can check that you'll get sine omega t. So the coherent states are those which go over to the classical solutions of the simple harmonic oscillator as h bar goes to 0. They're minimum uncertainty states, which I remind you is the condition for a quantum state to be as close to classical as possible, given the fact that you're in a quantum world. And moreover, they have the property that the expectation values of the observables match exactly what we would expect from our classical solutions of the simple harmonic oscillator. Let me just pause here and ask, is everything clear so far? Okay. Have you guys seen this before? No? Yes? Nobody's seen this before? Okay. Yes. A couple of people have seen this before. Yes?
Yeah. You said something about if it was a Gaussian and
Yes. So remember I think it was the second lecture of the course, I introduced the notion of a minimum uncertainty state as something which saturates the uncertainty bound. One of the things that you presumably remember is that a Gaussian is a minimum uncertainty state. And if a Gaussian is a minimum uncertainty state, then a shifted Gaussian is a minimum uncertainty state. If that's not clear, compute it. Okay. Compute the difference, the variance in x and the variance in p, and check that it's a minimum uncertainty state. It's a good exercise. I don't know if I just told you it was true or if I actually did the computation, but I think it was the second lecture of the course. Other questions? No other questions? Okay. Okay. So what is the relationship between the coherent states and the eigenstates of the Hamiltonian that we discussed earlier in this class? In particular, what is a coherent state? In the basis of states associated with the Hamiltonian. Well, we know that the eigenvalues of the Hamiltonian are a complete basis of states for the Hilbert space. So that means that the state lambda should be a linear combination of all of the possible energy eigenstates. Meaning that I could write it as some function of a dagger acting on the ground state. Any function of any state in the Hilbert space can be written as a function of a dagger acting on the ground state. If you want to understand why that's true, just imagine Taylor expanding the function of a dagger. So that's 1 plus some number, or sorry, I guess I should call it f0, some number f0 plus f1 times a dagger plus 1/2 f2 times a dagger squared plus ... acting on the ground state. And so you can see that the coefficients in the Taylor expansion here are just the coefficients of the state lambda when written in the basis of energy eigenstates. So this is a slick little way of writing down an arbitrary state in the simple harmonic oscillator Hilbert space compactly. So let's determine exactly what that function f is. How are we going to do that? Well, I'm going to use the defining equation that a acting on lambda is just a constant. So plugging in my expression above, I have a times f of a dagger acting on lambda. Acting on 0. I had it right the first time. So what is that? Well, a annihilates the ground state. So that can also be written as a commutator of a with f of a dagger acting on the ground state, because the second term in the commutator vanishes. And what is the commutator of a with some function of a dagger? Well, it's the derivative of that function, regarded as a function of a dagger. An easy way of seeing that is simply just to use this Taylor expansion here and ask what happens when you take the commutator with a. Well, f0, that term drops out because the commutator of a with a constant is 0. The first term will be f1 times the commutator of a with a dagger, known as 1. The second term will be f2 times the commutator, 1/2 the commutator of a with a dagger squared. So that's just equal to a dagger, because the 2 coming from the commutator of a with a dagger squared will cancel the 1/2 that appears right here, and so on and so forth. There was a question.
Yeah, just in the second last line, you have a lambda equals lambda acting on the lambda state. Should that be the ground state?
A lambda equals lambda acting on the lambda state. This equation, this is the defining equation of a coherent state.
I've written down on the ground state.
Oh, did I write it down incorrectly up above? No, I think I got it correct. Yeah. Good question. Other questions? This is a neat little trick that I'm using here. In a previous year, I assigned this as a problem in the problem set to derive what lambda looked like in the Fock space basis. And based on the results of that experiment, I'm doing it in class. Who says that theorists can't do experiments? So let's just compare this lower equation to this upper equation, and we see that the function f must obey a differential equation, that f prime is lambda f. Now, that's an easy enough equation to solve. It just tells us that f is equal to some constant times e to the lambda a dagger. So that the coherent state lambda is some normalization constant times e to the lambda a dagger, acting on the ground state. And in order to determine this normalization constant, let's just fix the norm of our coherent state to be equal to 1. So then this will be the square of that normalization constant. I suppose it could be the absolute value squared if I wanted that normalization constant to be complex, but the phase of the state doesn't matter, so I will just set it to be real. And then this is the expectation value of e to the lambda bar a times e to the lambda a dagger in the ground state. Remembering that lambda is complex, so I need to complex conjugate it when I write down the bra dual to the ket lambda. So this is n squared times just expanding out those two exponentials, the sum over n and m of lambda bar to the n, lambda to the m over n factorial times the expectation value of a to the m, a dagger to the m in the ground state. Excuse me. And the first thing that you see about this expression is that this expectation value vanishes unless n is equal to m. Because this is basically the overlap between the state of the energy eigenstate with eigenvalue n and the energy eigenstate with eigenvalue m. And eigenstates of a Hermitian operator with different eigenvalue are always orthogonal. If that's not clear, just work it out explicitly, and you'll see that in order to get this equal to 0, you just need to commute the a's through the a daggers in this expression. And unless you have exactly the same number of a's and a daggers, you'll have some a acting on the ground state left over. So you'll either have an a acting on the ground state 0 from the left, or an a dagger acting on the ground state from the right, both of which are equal to 0. So this is n squared times the sum over n and m. Sorry, the sum over n now, because we're setting n equal to m, of the absolute value of lambda to the 2n power over n factorial squared times the norm of the state a dagger n acting on the vacuum, which is something that we discussed earlier and is just equal to n factorial. Just because a dagger acting on the ground state is not the nth energy eigenstate unit normalized, but rather 1 over n factorial times that. So that cancels one of the n factorials in the denominator, and we're left with a sum that we know how to do. It's just the exponential of the absolute value of lambda. So that this normalization constant, in order for the state to be unit normalized, is e to the minus lambda squared over 2. So, putting this all together, the coherent state lambda is given by a normalization factor to make the state unit normalized of e to the minus the norm of lambda over 2 times e to the lambda a dagger acting on the ground state. Or, if we wish to write this out in terms, explicitly, in terms of the eigenstates of the number operator, it's the exponential of minus lambda squared over 2 times the sum over n of lambda to the n divided by the square root of n factorial times the nth number operator, eigenstate. Again, all I'm doing here is using the Taylor expansion for the exponential and the fact that a dagger to the n acting on the ground state is 1 over the square root of n factorial times the nth number operator eigenstate. Any questions on this so far? Yes?
I missed why a coherent state is very similar to a classical.
Why is a coherent state similar to a classical state? Well, for 2 reasons. The first is that it's minimum uncertainty state. Okay. We always think of minimum uncertainty states as being as close to classical as possible, because they're the states for which we minimize the variance in x and p, subject to the fundamental quantum constraint that h bar is non-zero. And second, and more importantly, the fact is that the observables that you compute in the minimum uncertainty state evolve exactly like the observables of a classical harmonic oscillator. So one of the confusing things about the energy operator ground states is that the observables x and p don't evolve at all, okay? Because that's the definition of an energy eigenstate. They're things that don't evolve in time. So we really constructed these states because we were looking for states where the outcome of observations will, in the semiclassical limit, match with what we expect from the simple harmonic oscillator, namely that we have a state which is evolving in time in some oscillatory manner. Okay? So when I write down this fact 2 here, what I'm really pointing out is that the outcomes of observations, namely if you measure the position at a given time, will be given precisely by the classical formula. Good question. I hope that's clear. Any other questions? Okay. Let me just make a comment about this formula, which will help us understand a bit more intuitively what it means to be in a coherent state. So, if I look at this relationship between the coherent state and the set of eigenstates of the Hamiltonian, or the number operator, you see, of course, as we anticipated, that lambda is not an energy eigenstate. And in fact, the set of all coherent states form a different basis for the Hilbert space of the simple harmonic oscillator. And in fact, it turns out that it's not an orthonormal basis. We usually like working in terms of an orthonormal basis because it's convenient. But for other purposes, we're saying that sometimes non-orthonormal bases are useful. And in order to understand a bit more the physics of one of these coherent states, let's imagine that you're in a coherent state and you measure the energy of the system, which is to say you measure the expectation value of the number operator. And then what you will see, according to the usual Born rule, is that the probability of being in the nth state after the outcome of this measurement is proportional to the absolute value squared of this guy right here. So it's proportional to, well, let's just say it's equal to e to the minus lambda squared times the expectation value of lambda times the square of lambda to the 2n divided by n factorial. In fact, this function has a name. It's one of the most famous functions in statistical physics. It's called the Poisson distribution. If I were to graph the probability of being in the nth state as a function of n, you would find that for a fixed value of lambda, the probability of being in the ground state will be rather low, and the probability of being in the nth excited state at low n will increase as a function of n because of the lambda to the 2n factor. But then, at some finite value of n, it will turn around, because at some value of n, the e to the minus lambda squared, the n factorial will take over. And so if you just think about how this function lambda to the 2n over n factorial behaves, it's clear that at small values of n, it should increase because of the lambda to the 2n. But then for values of n that are of order lambda, the n factorial term will start making this this factor decrease as a function of n. So you'll expect that there'll be some local maximum, so that there will be a peak at some value of n bar, at some value of n, which I'll call n bar. So the coherent states are not exactly energy eigenstates, but in terms of the energy eigenstate basis, they're peaked around some finite value of the energy. Question?
This function is with the absolute square root of n lambda?
Absolutely. This function is the absolute value of the overlap between n and lambda squared.
So,
To see that, just remember that the n's are unit normalized, so all you're doing is you're picking out this term right here.
yeah. So what does it mean? Because we're in the state lambda, well, the system is in the state lambda, and
Yeah.
we're calculating the probability of the system in the state lambda being in the state lambda.
Well, remember, the third postulate of quantum mechanics says that if you're in a given state and then you observe, you make a measurement, meaning that you make an observation, then the probability of observing then the outcome of that observation will be one of the eigenstates of that operator. So you'll get an eigenstate of the energy operator. So you'll get h bar omega times n plus a half. And the probability of observing the result n is given by the square of this overlap vector. Other questions? So it's a fun calculation to estimate the value of this peak n bar. Yes, question.
I guess, how did you know that the coherent states form a complete?
Oh, I haven't proven that to you. That's something that you might prove on your next problem set. Okay. You also might not prove it on your next problem set. I don't remember. But it's just a fact. Okay. I'm a very important person, so you can believe me when I tell you things. Okay. So that's a fact. Okay. Yeah. Whenever I use the word fact and then put a colon after it, that means it's something that you're supposed to believe that I'm not, but I'm not going to bother to prove it to you. It's not hard to check, actually. Basically, I mean, it depends on what you mean by proof. Okay. Technically, this is a statement about square normalizable wave functions being expandable in terms of these, in terms of the wave functions for lambdas that I wrote down above that were these Gaussians. So it's a statement that all of the states in the Hilbert space can be written as sums of Gaussians. Okay. Intuitively, it seems plausible that if you have some arbitrary wave function that looks like this, you could write it as a little Gaussian here, plus a little Gaussian there, plus a little Gaussian there, plus a little Gaussian there, and so on and so forth. That's the sort of proof that I would give if I were asked to prove it. A mathematician wouldn't be happy with that proof, and they would talk about silly things like partitions of unity or something like that. If you want to be a mathematician, you can prove it as a mathematician would. Then it's some statement about functional analysis. So yeah, that was a fact, meaning that it's something that I say that you're supposed to believe, but that I haven't necessarily proven to you. Good question. Keeping me honest here. Okay. So just for fun, let's go ahead and calculate this value of n bar. which is the value of the energy, the typical value of the energy that you would observe in some coherent state. In terms of our classical intuition, this would tell you roughly the amplitude of the oscillator. Remember that the energy of an oscillation in classical physics is proportional to the square of its amplitude. If x is a sine omega t, the energy goes like a squared times omega squared. Okay, so how do we compute it? Well, we need to set p prime of n equal to 0 in order to compute n bar. So let me write down an approximate expression for p. So because I'm computing its derivative, I can ignore this overall constant out front, e to the minus lambda squared, if that's not going to affect the derivative with respect to n. And I'll write down log p. So that's 2n times the log of the absolute value of lambda minus the log of n factorial plus a constant that is independent of n. And using Stirling's approximation, this is log of n factorial is well approximated by n times log n minus 1. And so the derivative of p with respect to n is equal to 0 precisely when the derivative of the log of p with respect to n is equal to 0, which will occur when 2 log absolute value of lambda minus the derivative of the second term in parentheses, which is just log n, is equal to 0, so that n bar, the place where this is equal to where this derivative is equal to 0, is just equal to the absolute value of lambda squared. As one might expect, as you increase the absolute value of lambda, remember that the wave function of a coherent state is a displaced Gaussian, and the amount of displacement away from the origin is proportional to the square of lambda. That's what I call x naught 0. That's what I call x naught 0. And so intuitively you would expect that as you take a harmonic oscillator, you drag it farther from the origin at x equals 0, the force is larger, the energy is larger, and indeed that's exactly what we're seeing here. This is a great little example to think about because we can really make contact with classical physics from our quantum mechanical understanding. And then one can calculate the height of... yes, question?
Sorry, what are you saying at log p?
Let me write that a little more explicitly. The derivative of the log of... There's a prime there, by the way. So prime is d by dn. And the derivative of log p is 1 over p times the derivative of p. So if p prime is equal to 0, then the derivative of the log of p is equal to 0. So let's just compute the value, value of p at its peak. So this is the exponential of just rewriting this formula up here. So that's the exponential of minus lambda squared. Then we have this term down here, which I'll exponentiate. So that gives us n times n bar times log lambda squared minus the log of n factorial, which is minus n bar times log n bar minus 1. Okay, let's see if I've done this correctly. So if I've done this correctly, because n bar is lambda squared, this term will cancel this term. And we're left with 1. That's not quite right. I must have made a mistake somewhere. Because I forgot a 2, maybe? Did I forget a 2? No, this is right. This is right. So what does this mean? This means that in the limit where Stirling's approximation is valid, which is to say large n bar, which is lambda squared, the probability of observing an energy n bar is just equal to 1. Any questions on this? I should mention that there's a reason why I went through this computation, which is that the minimization of a Poisson distribution and the computation of the probability at its peak is one of the most important computations that we do in physics. Okay? It appears all over the place in particle physics, condensed matter physics, statistical physics, and if you haven't seen, and so this cancellation here is responsible for some very famous effects in physics. Okay? So I think it's worth seeing at least once. Okay. I've got about 20 minutes left, 25 minutes left, which is just enough time for me to explain to you why considerations of this sort can explain the origin of structure in the universe. So what we've seen here is that one can obtain a minimum uncertainty state by simply writing down a shifted ground state of the harmonic oscillator. And this will be a minimum uncertainty state independent of the frequency of the harmonic oscillator. So, for example, you could write down some other state which I'll call D in order to distinguish it from the states that we were considering above, which is a Gaussian centered around the origin, but with a width that is not necessarily set by the frequency of the harmonic oscillator that we started with. So we could imagine, for example, that if you're studying a harmonic oscillator with a given frequency, you could also define some different state, which is a Gaussian, but with a width d that differs from that of our simple harmonic oscillator ground state. So if you wanted to draw a picture of what this state looks like, so if you were to plot the wave function of this state, so if here is the harmonic oscillator potential, then drawn as a function of x, then your ground state might look something like that dashed line. But the state D could look something like that solid line. And because of this picture here, you should think intuitively that what we're doing is we're taking the wave function and squeezing it, which is the origin of the name for this sort of state, namely that it's a squeezed state. How do we understand the description of these squeezed states in terms of our simple harmonic oscillator Fock space basis? Well, D is a Gaussian. So in particular, it is the ground state of a harmonic oscillator, but it's the ground state of a simple harmonic oscillator with different frequency. With some frequency omega prime, that would be h bar over m times d squared. Just comparing our definition of the state in terms of its wave function to the wave function of a simple harmonic oscillator. So, why are squeeze states relevant in physics? Well, squeeze states are relevant in physics for the following reason. So, let's imagine that we start with a simple harmonic oscillator with frequency given by omega prime, and then we suddenly change the potential, meaning that we change the frequency to omega. Then the wave function is a continuous function of time. So if we make the change in the potential instantaneous, then immediately after we change the potential, we will be in a state D. Namely, the state of the harmonic oscillator ground state before you change the frequency. And this sort of process, where you take a harmonic oscillator and you change its frequency as a function of time, is a prototypical time-dependent situation. Remember that physics is just harmonic oscillators. So if you want to study a prototypical system where some Hamiltonian is changing as a function of time, then the simplest possible system you could study is a harmonic oscillator whose frequency is changing with time. And in that simple case, the simplest case would be one where the frequency changes instantaneously. So for that reason, what we want to understand is how to write the squeeze state D in terms of the energy eigenstate basis of the simple harmonic oscillator with frequency omega rather than omega prime. Because that will tell us what the physics of the squeeze state looks like at late times, after the potential has changed. Question?
Yeah, I was just confused because omega prime is the frequency of the state D. And
well, sorry. That's not a correct. There, okay, good. Yeah. The point is that the simple harmonic oscillator with frequency omega has a ground state which is Gaussian with some width. The width of that Gaussian is determined by the potential. It's determined by omega. Okay. If you want to write down some other Gaussian, any Gaussian you write down that's centered about the origin is the ground state of some harmonic oscillator. Okay. So that means that if you want to write down an equation for the state D, then the equation is that the state D is annihilated not by A, which is the annihilation operator of a simple harmonic oscillator with frequency omega, but A prime, which is the the lowering operator of a simple harmonic oscillator with frequency omega prime.
So you've written that we're going to start with frequency omega prime.
Start with frequency omega prime and the system in its ground state. Okay. Then immediately change the frequency to omega. The wave function, right after you make that transition, doesn't have time to react to the change in the potential. Okay. So if you really imagine that the change in the potential is a delta function, then the fact that the wave function is continuous means that immediately, after time t equals 0, when this transition takes place, the state is still going to be in the squeeze state D. Okay. And now I want to understand what that looks like from the point of view of the late time oscillator with frequency omega. Yes?
would doing this be different than just writing the state D in terms of a linear combination of states?
That is exactly what I'm about to do. So let me proceed and, yeah. It turns out that D is not a coherent state as such. It's actually slightly different. So in order to see that, what we need to do is relate A and A dagger to A prime and A prime dagger. Now, A prime is a linear combination of X and P, and A is a linear combination of X and P. But they have, there's an over M omega prime here, of course. But because of the factors of omega versus omega prime, they're not the same linear combination of X and P. So what you will find is that A prime is not equal to A, but it can be written as a linear combination of A and A dagger. And likewise, A prime dagger will be a linear combination of A and A dagger. And of course, the coefficients will be related by complex conjugation, just because A prime dagger is the Hermitian conjugate of A prime. The relationship between the raising and lowering operators for harmonic oscillators at different frequencies are known as Bogoliubov relations. And in the present case, it's easy enough to compute exactly what alpha and beta are. How would you go ahead and do that? Well, so for example, for this first equation, just take the definition of X in terms of A and A dagger. So X is H bar over 2M omega times A plus A dagger. That's just the definition of A. Okay? And so X is like the real part of A, and P is like the imaginary part of A. So you could then just take these two formulas for X and P, plug them into the formula for X prime to determine what the coefficients alpha and beta are in this expression. And that's a simple exercise. So I'll just tell you the answer. So alpha and beta are linear combinations of the ratios omega over omega prime. Sorry, let me write that a little more neatly. So why is this useful? This is useful because it allows us to determine exactly what the squeeze state looks like in the harmonic oscillator basis with frequency omega. Because in terms of A and A dagger, the state D is the ground state of A prime. So A prime acting on D is equal to 0, which is just going to be the statement that in the A and A dagger basis, A plus beta over alpha A dagger acting on D is equal to 0. So, as before, we can use this equation to determine exactly what D is. So let's use the same trick we used before. So let's let D be some function of A dagger acting on the ground state. Then this relationship here will turn into a differential equation for F, so that A leads to an F prime. So F prime plus beta over alpha A dagger times F should be equal to 0. So F is a function such that when you take the derivative with respect to A dagger, you get beta over alpha times A dagger times that function. Does anyone know the solution of that equation? I'll give you a hint. We've already seen it twice today. Okay? You take the derivative with respect to a dagger. So here prime is d by d a dagger. You take the derivative with respect to something, and you take the derivative. Okay, I'll give you a hint. What if instead of a dagger, I were writing that equation for x? So d by dx of some function is x times that function. Okay, hopefully that's ringing a bell. That's the equation of motion. That's the equation that for the Gaussian of the simple harmonic oscillator ground state. Okay. So that means that f is going to be some overall constant times e to the a dagger squared with a coefficient beta over 2 alpha. So that the squeeze state in the simple harmonic oscillator basis with frequency omega is some normalization constant times e to the beta over 2 alpha a dagger squared acting on the ground state, or in terms of these number operator eigenstates, the sum over n times beta over 2 alpha to the 2n times 1 over the square root of 2n factorial. That's just that same normalization factor times the state with number operator eigenvalue 2n. And it's a sum of n equals 0 to infinity. Is this set of manipulations clear? Have I lost everyone? Have I only slightly confused everyone? Slight confusion is a good thing to aim for. It builds character. One of the things that often confuses people is the fact that I'm thinking about not functions of x and p, but functions of a dagger and a. Okay. That shouldn't perturb you too much. In quantum mechanics, x and p are operators. They're on exactly the same footing as a and a dagger. So if you're going to allow yourself to think about functions of x and p as operators, you should allow yourself to think about functions of a and a dagger as operators. Different choices of different problems will be easier or more difficult to solve in different bases. And what we're seeing is that if the problems that we solve are trying to understand the time evolution of the state of a harmonic oscillator, whose frequency changes suddenly in time, then the x and p basis is not a particularly intelligent basis to use, and instead we should use an a and a dagger basis. And writing out the differential equation in terms of x and p is no more or less allowed in quantum mechanics than writing out differential equations for a and a dagger. Any questions? Let me make a few comments about the interpretation of this formula. The first thing that I should comment is that only even energy states appear in this expansion of the squeeze state D. Why is that? Well, I remind you, as you presumably already know, that the energy eigenstates of the simple harmonic oscillator with even number are even functions of x, and those with odd number are odd functions of x. The ground state is symmetric in x. The first excited state is antisymmetric under x goes to minus x, and so on and so forth. The squeeze state that we started with was symmetric in x. It was parity even, to use a terminology that we'll discuss more later on in this class. And because the original state was parity even, the final state is parity even. So this is an example of a consequence of something that will occupy us in more detail later on in this course, namely a symmetry of the system and of the states under parity symmetry. This is a simple example of a conservation law due to a symmetry. The harmonic oscillator, and even when it's time dependent, if only the frequency is changing, it preserves parity symmetry. So if your initial state was parity symmetric under x goes to minus x, so is the final state. And second, if one were to imagine this process where the frequency changes suddenly in time, and then we were to measure the energy of the state, we would find P of n by, again, computing, as with the coherent state, the absolute value of this coefficient here. And we would find that it is, again, a Poisson distribution. But it's a Poisson distribution not on all states, but a Poisson distribution on even states. And it will have a peak, which can be computed exactly as before. So n bar will be, so remember that for the Poisson distribution, the peak was the, so let me just remind you up above, the peak of the Poisson distribution was the absolute value of lambda, and the thing that's playing the role of lambda here is that ratio beta over 2 alpha. So the peak is at the absolute value of beta over 2 alpha squared, or in terms of the frequencies, just plugging in the expressions for beta and alpha that I wrote up here, it's just omega squared minus omega prime squared over omega squared plus omega prime squared, all squared. So you can see, just by looking at the numerator of this formula, you have the difference between omega squared and omega prime squared. So if the frequency changes by a lot, then that implies that even though you started out in the ground state of an oscillator with frequency omega, you're going to end up, most likely, in a state with very high energy of the state omega prime. Let me state that again. It says that if you start in a state with nothing there, you're in the ground state, lowest possible value of energy, you suddenly change the frequency of the harmonic oscillator, then you end up in a state with a lot of energy. Okay. Let's consider the universe. In most of the models of cosmology that we understand, the universe, for all we know, seems to have started in a state with not much there. But then the size of the universe changed rapidly in time. The dynamics of the fundamental degrees of freedom that describe the particles of our universe are described by harmonic oscillators. Everything's described by harmonic oscillators. Remember, the first sentence of this lecture was that physics is that set of human experience that is described by coupled harmonic oscillators. And so if you want to model the changing size of the universe, what that means is that the potential of the harmonic oscillator was changing in time. Its frequency was changing in time. So, if you have a universe with not much in it, but then the universe expands rapidly, the frequency of these harmonic oscillators is changing rapidly, and you end up with lots of stuff, okay? And we give a name to that stuff. That stuff is us. Okay. I think it's not an exaggeration to say that this is the basic physics behind what we believe is the origin of structure in the universe. So, for example, if you study the theory of cosmological perturbations, then it essentially involves the calculation that I've just described. Now, we have to dress it up a little bit, okay, because it's not one harmonic oscillator, it's an infinite number of harmonic oscillators. It's not a frequency of the harmonic oscillator that's changing, but rather the universe in which the harmonic oscillators live that's expanding. And it's not expanding instantaneously. It's expanding with some time dependence, which is very complicated. It depends on the matter that's present, and blah, 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 blah. But the basic feature is precisely that which we have described. When you change the potential, if you have a particle and a potential, you change the potential by a lot very rapidly, then a state with no energy suddenly gets a lot of energy. I should also mention that squeeze states appear in other areas of physics. In optics, in fact, is the area of physics in which they were first really studied, but they also appear all over the place. Dense matter physics, for example. Let me stop here and see if there are any questions. Yes?
So I don't understand when you have
F prime. Good. Yeah, I went a little fast here. Okay. Let's go through that in a little bit more detail. Okay. So let's just use this equation here. So what does that say? That says that A plus beta over alpha A dagger times F of A dagger acting on the ground state is equal to 0. Okay? So what we do is we then take this A and we commute it through that F to make it hit the ground state. When it hits the ground state, you get 0. So you're just left with a commutator of A with F, which is F prime. So of A dagger plus beta over alpha F of A dagger acting on the ground state is equal to 0. Okay. Meaning that that F has to satisfy this particular differential equation. Remember, F is a function of A dagger. So F can never annihilate the ground state. Only A can annihilate the ground state. So the only way that that equation could be satisfied is if F solves a particular differential equation. It's a sort of dirty trick that I'm using in order to do these calculations, but physics is a collection of dirty tricks like this. Any other questions? Yes?
Should there be a negative in your exponent?
Probably. Yeah, surely. Thank you. Sorry about that. Is that why everyone was so confused? You really need to tell me these things when I make typos like that. They're not typos, I'm not typing. When I make mistakes like that. Okay. Good. Well, if there are no other questions, I'll see you guys on Friday, where we will learn about the WKB effect and